Hello everyone, welcome to this lecture. The plan for this lecture is as follows. In this lecture we will discuss various operations that we can perform on graphs. We will see various mechanisms of representing graphs. We will discuss the graph isomorphism problem and we will define the connectivity in a graph. Okay, so it turns out that since graph is nothing but a collection of two sets, we can perform various set theoretic operations on a graph and obtain new graphs. So let us discuss some of the important operations which we can perform on the graphs. So we will first define what we call as the subgraph of a graph. So if you are given a graph G with the vertex set being V and the edge set being E, then a graph H with vertex set W and the edge set F will be called as a subgraph of G if the vertex set W of H is a subset of the vertex set V of G, namely all the vertices of H should be the vertices of G, and the edge set F of H should be an edge set should be a subset of the edge set E of G. That means all the edges of F should be present in E. Okay, so that's a simple, straightforward definition of a subgraph. Now let us next define what we call as a proper subgraph of a graph. So we will first give intuitive definition, what exactly we can think of a proper subgraph, and then we will see that definition is not correct, right? So remember, when we define the proper subset of a set, we say that A is a proper subset of B if A is a subset of B and there is something extra which is always there in B, which is not there in A, right? So let us try to extend that definition in the context of a proper subgraph. So say my definition is that graph H will be called as a proper subgraph of G if either the vertex set of H is a proper subgraph, it is a proper subset of the vertex set of G, or the edge set and the edge set of H, it's a proper subset of the edge set of G. Suppose that is my definition. Now, if this is my definition, then with respect to this definition, if I take my graph G and H to be this, then H won't be considered uh, as a proper subset of G. This is because all the vertices of H are the vertices of G as well. So this condition that W being a proper subset of the subset V is not satisfied, right? So as per this definition, I will say that H is not a proper subgraph of G, but this is a proper subgraph of G because there is something extra in G which is not there in H. Namely, the edge between the vertex B and C is there in G, but that is not there in the graph H. So that means the definition that I gave here is not the correct definition. So that's why the right definition of the proper subgraph is the following. I will say that H is a proper subgraph of graph G if it is a subgraph of G, because that is definitely the requirement, and it is such a subgraph that it is a subgraph which is different from the graph G or the parent graph. Okay, if that is the case, then I will say that my graph H is a proper subgraph of the graph G. Okay, so this condition that G is not equal to H takes care of the fact that there is something extra in the graph G which is not there in the graph H. Now let us next define what we call as induced subgraph. So if you are given a graph G with vertex set V and edge set E, and if I take a subset of vertices W, then G prime is called the induced subgraph, or the induced by the vertex set W, such that the vertex set of G prime is W and the edge set E prime of G prime consists of only those edges whose both the endpoints are within the subset W. So basically what this induced subgraph tries to do is the following. You are given a collection of vertices W. That W could be empty or it could be the entire set of vertices V. So you are given some subset W and you are focusing only on that part of the graph G where all the edges have endpoints within the subset W only. Even if Whereas all the edges where one of the endpoints is outside the subset W, you are not focusing on those edges. Okay, so that's the definition of the induced subgraph. So its vertex set will be W, and edge set will be only those edges. Okay, so sorry for the typo here. This should be Vi, comma Vj, not Ei, comma Ej, such that both the endpoints are member of the subset W. Okay. So for instance, if this is my graph G, and if I take my W to be the subset B comma C, then I am focusing only on that part of the graph G where the edges have their endpoints restricted within the subset W. Okay, so that means I can't take this edge. This edge is not allowed because one of the endpoints is A, and that A is not within my subset W. Similarly, I cannot take the edge between A and C because one of the endpoints of this edge is the set A, which is not there in my W. Whereas if I take my W to be the node A only, then I get an empty graph. Empty graph in the sense which has no edges, because this edge won't be there as B is not within my W. This edge won't be there because the node C is not within my W, and this edge also won't be there. Right. So now let us see some set theoretic operations that we can perform on a graph, on an existing graph, to get new graphs. So imagine you are given a graph, then the deletion of an edge is denoted by this operation. So imagine small e is an edge. So if I delete an edge, then the vertex set does not get disturbed. It remains the same. It's only the edge set which gets affected. That means my new edge set will be the old edge set minus the edge e which I am excluding. Whereas if I am removing a collection of edges, even in that case, my vertex set remains intact. It's only the edge set which gets affected. That means my now new edge set will be the difference of the old edge set and the edge set E prime, which I am deleting from the graphs. So it's like saying the following. Imagine your graph represents a computer network where the nodes are the computers and the edges represents a cable connecting two computers, right? So if you remove a cable, that does not mean that the corresponding computers also get deleted, right? The computers are there, still there, it's only the cables which are getting removed. Similarly, if I add a new edge that it is expressed by this operation, then my edge set gets affected. So I will be including a new edge. Okay. Of course, if it is okay, so I will be including a new edge, and the endpoints of the edge small e will be included in my vertex set. Okay. On the other hand, if I delete a vertex from my graph G, then definitely the vertex set gets affected and also the edge set gets affected. So I have to remove all the edges whose one of the endpoints is V from my graph. So it's like saying the following. Again, if I take the fact that uh, my graph represents a computer network, then deleting a vertex is equivalent to saying that I am deleting or removing a computer itself from my network. So if I remove a computer from the network, then whichever cables has one of its endpoint as that computer, those edges won't be there anymore in my computer network, right? So I have to modify my edge set as well. Whereas if I remove a set of vertices V prime, then my new vertex set will be the difference of the old vertex set and the vertex set V prime, and edge set E prime will be the following. I have to remove all the edges where one of the endpoints of the edge is in my subset V prime. Okay, so let me demonstrate these operations with respect to this graph. So imagine this is my graph G. If I remove the vertex A, then this edge E1 and edge E3 will no longer be there, and I will get this reduced graph. Whereas if I remove the cable connecting the node A and node B, or the computer A and computer B, then only the edge E1 vanishes. The vertex set remains the same. Okay. Now let us discuss the various data structures that we can use to represent graphs. And people who have studied data structure, they must be knowing two of the common representations that we use to represent graphs. So again, I am explaining in the context of undirected graph, but you can easily generalize this data structure to represent directed graphs as well. So we have what we call as the adjacency matrix representation. So this is a Boolean matrix. So if your graph G is consisting of vertex set V and edge set E, and if the cardinality of the vertex set is n, then this matrix is an n cross n Boolean matrix, and the I comma jth entry is 1 if and only if Vi and Vj are the endpoints of some edge in your graph. Otherwise, it will be 0. Okay. And this representation is preferred for dense graph. What do we mean by dense graph? A graph which has a lot of edges. That means it's not the case that you have very few edges. That means you have lots of edges in the graph, in which case uh, a majority of the entries in your matrix will be 1. Okay. Whereas a sparse graph is a graph which has lots of vertices but very few edges. For such a graph, the adjacency list is the preferred data structure for representation of the graph. So what is this adjacency list? So it is a collection of linked lists. Each link, so basically a collection of n linked lists. So you will have the first linked list with V1 as the starting node, second linked list as with V2 as the starting node, and like that Vn nth linked list with Vn as the starting node. And in V1, you will now link all the nodes which are incident. You link all the nodes which are the endpoints of an edge with V1 as one of the endpoints. That means in your graph G, right, you focus on the edges which has V1 as one of the endpoints. So for those edges, find out the other endpoints and you you put them in the linked list with V1 as the endpoint. So basically the linked list starting with V1 lists down all the neighbors of V1. Similar to the linked list with V2 lists down all the neighbors of V2 and so on. So now you can see that why this representation is very popular for representing sparse graph. That means it graphs which has only a very few edges. If you have very few edges, then the size of each linked list will be very small. You don't need a huge matrix with lots of entries being zeros and only few entries being 1, right? So these are the two popular representations for representing an undirected graph. They can be used even for representing directed graphs as well. And there is this third data structure, which is called as the incidence matrix. So what is this incidence matrix? It is so again I am explaining assuming an undirected graph. So this will be a matrix which will have cardinality of V number of rows and cardinality of E number of edges, and it basically represents the relationship between the edge and its endpoint. Okay, so what it means is the following: if you have an edge E with Vi and Vj being its endpoint, then the entry number Vi comma E and the entry number Vj comma E will be 1. Otherwise, and the remaining entries will be 0. So for instance, if this is my graph G, okay, so there are 3 vertices, so 3 rows, and there are 3 edges, so 3 columns. What are the endpoints of E1? The endpoints of E1 are A and B. So under the column E1, I only mark the entry for A row and the B row as 1 to show that the endpoints of the edge E1 are A and B, and all other column entries under E1 will be 0. Similarly, the endpoint of E2 are B and C. So only the entry in row number B and column number E2 will be 1, and entry in row number C and column number E2 will be 1, and all other entries in column number E2 will be 0, and so on. Okay, so that's the incidence matrix. Okay. Now let us define graph isomorphism. So if you see these two graphs, pictorially they are drawn in a different way. Okay, so the first graph is a rectangle, whereas the other graph does not look like a rectangle graph, because you might be saying that there are two edges which are crossing each other, right? But if you see closely, structurally they are similar graphs. What do I mean by structurally they are similar graphs? So both the graphs have the same number of nodes, namely 4, same number of edges, namely 4 edges, and even though the vertex names are different in the two graphs, so if I call this as graph G1 and this as graph G2, the name of the vertices of G1 are A, B, C, D, whereas the name of the vertices of G2 are V1, V2, V3, V4. So you will say that how can they be the same graph, because the vertex names are different. If I don't focus on the name of the vertices and the name of the edges, but mentally think in my mind whether there exists a one-to-one correspondence between the vertices of the graph and the edges, then I find that the two graphs are structurally same. What does that mean? If I think in my mind that vertex A of G1 corresponds to vertex V1 of graph G2, and if I consider vertex B of graph G1 corresponding to vertex V3 of G3, then you can see that there exists an edge between A and B in graph G1, and similarly I can consider this edge as the edge E1 between the mapping of A and the mapping of B. Similarly, this node C I can associate with the node V2 here, right? And you can see that if that is the case, then the edge E2 in the graph G1 corresponds to the edge E2 of this graph G2, and so on. So in that sense, they are structurally same graphs, but drawn in a different fashion. Okay. In the same way, this graph G1 and this graph G2 are structurally same, right? So the node 1 of graph G1 corresponds to the node A of graph G2, and so on. And you can then verify that structurally, if I reinterpret graph G2, then I can redraw it in the same way as the graph G1. Okay. So in that sense, these pairs of graphs are isomorphic. They are structurally drawn different. They are drawn differently, but structurally they represent the same information. That means I can always redraw one of the graphs as other graph. Okay. So how do I formally define whether two graphs are isomorphic or not? So imagine you are given two graphs G1 and G2. They are called as isomorphic, and isomorphic graphs are represented by this notation. So I will say that the two graphs are isomorphic if I can define a bijective mapping between the vertex at V1 and the vertex at V2, right? Such that the following holds. If you have an edge between the node U and V in the first graph, then you focus on the mapped U vertex in G2 and the mapped V vertex in G2, and there should be an edge between the mapped U vertex and the mapped V vertex in E2 as well. And this implication is by implication. That means other way around should also hold. Okay. So if you can find one such mapping, one such bijection between the vertex sets, then we will say that our graph is isomorph, the two graphs are isomorphic, and the isomorphism is denoted by the bijection. Okay, so when we say that, okay, show me an isomorphism between graph G1 and G2, basically I am asking you to show the one-to-one correspondence between the two vertex sets, but namely the vertex set of G1 and the vertex set of G2, such that this by implication is true. Okay, so the graph isomorphism problem is the following. You are given two graphs G1 and G2, and you have to check whether they are isomorphic or not. Checking whether they are isomorphic or not is equivalent to checking whether there exists a bijection between the vertex sets of the two graphs such that this by implication is true. So what will be the naive algorithm to check whether two given graphs are isomorphic or not? If the cardinality of the vertex sets of the two graphs is n, okay, by the way, a simple necessary condition for the two graphs being isomorphic is that they should have the same number of vertices. If one graph has more number of vertices than other, how at the first place they can be isomorphic? They can never be isomorphic. So imagine that the vertex set of both the graphs is of cardinality n, then a naive algorithm to check whether the two graphs are isomorphic is to try all possible n factorial bijection between the vertex set V1 and the vertex set V2, and for each of those bijections check this implication is true or not. Even if you, so indeed if the two graphs are isomorphic, one of these n factorial bijections will satisfy the by implication, and hence you can declare that the two graphs are isomorphic. But if all the n factorial bijections fail to satisfy this by implication, you will say that the two graphs are not isomorphic. But then what is the running time of this algorithm? You have to try n factorial bijections, and n factorial is an enormously large quantity. So that's why this algorithm, this naive algorithm, will work only for small values of n, and it's still a big open problem to come up with efficient algorithms or feasible algorithms to check whether two graphs are isomorphic or not. Okay. So how do we verify whether two graphs are not isomorphic or not, right? And we can verify whether two graphs are not isomorphic or not by checking for graph invariant properties. So what are graph invariant properties? They are the properties which should be preserved by isomorphic graphs. Okay, that means these are the properties which should be there both in graph G1 as well as in graph G2 if at all they are isomorphic. That means if any of these properties is violated, then you can declare that the two graphs are not isomorphic. So some of the naive graph invariant properties which should be preserved by the isomorphic graphs are the following. They should have the same number of vertices, same number of edges, number of vertices of a particular degree should be same in both the graphs and so on. So for instance, if your graph, if in your graph G there are G1 there are two vertices of degree 2, then in G2 also there should be exactly two vertices of degree 2, right? Otherwise the two graphs can never be isomorphic, because you would like to associate a vertex of degree 2 in G1 with another vertex of degree 2 in G2 and vice versa, right? However, so it turns out that if any of these graph invariant properties is violated, then you can immediately declare that the two graphs are not isomorphic. However, it turns out that the graph invariant properties are only necessary condition for the existence of isomorphic graphs. Okay, right? And we don't have an exhaustive list of graph invariant properties, right? We don't know that, okay, all these properties, or you don't have a list of properties such that if those properties are preserved both in graph G1 and G2, then you can declare that the two graphs are isomorphic. Unfortunately, we don't have such graph invariant properties. So for instance, if I take these two graphs, G1 and G2, then it's slightly difficult to identify a graph invariant property which is present in G1 but not present in G2, right? In fact, the graphs G1 and G2 here are not isomorphic, and we have to identify here a graph invariant property which is present in one graph but not present in the other graph. Okay, So if you see closely here, if at all graph G1 is isomorphic to graph G2, then I need to associate the vertex A of G1 with some vertex in G2. And that association could, the vertex which could be associated with vertex A could be either the vertex T or the vertex U or the vertex X or the vertex Y. Why so? Because the degree of A here is 2. So it could be associated, it can be associated only with a vertex of degree 2 in G2. And the only vertices of degree 2 in G2 are T, U, X and Y. You can't associate vertex A with vertex S because A has degree 2 where S has degree 3 and so on. But it turns out that in graph G2, the vertex T, the vertex U, the vertex X, the vertex Y, all of them are adjacent to another vertex of degree 2. Okay, so for instance, if you take T, T is adjacent with U and U has degree 2. If you take U, U is adjacent to T and T has degree 2. If you take X, X is adjacent to Y, which has degree 2, and similarly Y is adjacent to X, which has degree 2, right? But if you see graph G1, all the neighbors of the node A, they have degree 3. So B has degree 3 and D has degree 3. So that means this is now a graph invariant property which is present in G2 but not present in G1. The graph invariant property is that all the vertices of degree 2 in G2, they have a neighbor which also have degree 2. But that property is not satisfied in G1. Namely, I have a vertex of degree 2, namely the vertex A, and none of its neighbor has degree 2. So that shows that I can never find out a isomorphism or a bijection between the vertex set of G1 and the vertex set of G2 because I can't find a vertex corresponding to the vertex A in the graph G2. Okay, right. Now let us next define the connectivity in a graph. So for that we first recall the definition of a path of length n between a node U and a node V in a undirected graph where n is a non-negative integer. So a path of length n between the node U and the node V is a sequence of n edges in the graph, and say the edges are of the form x0, x1, x1, x2, and continuing like that, xn minus xn, such that the starting vertex or the first or the first endpoint of the edge E1 is U and xn is equal to V. Okay, if that is the case, then I say that I have a path of length n between the node U and the node V. Okay, so remember there is no restriction on whether the edges in this sequence of n edges they are distinct or they are allowed to be repeated or not. Right? No such restriction is there when I consider a path of length n. A path is also called as a walk from U to V because we are just traversing the edges and going from the node U to node V. If the starting vertex U and the end vertex V of the path are same, then the path is also called as a circuit or a closed walk. And if all the edges in my path between U to V are distinct, that means no edges are repeated, then I call the path as a simple path. And if I have a circuit where the starting vertex and the end vertex are same, and if all the edges are distinct, then the circuit is called as a simple circuit. By the way, in a simple path, the vertices are allowed to be repeated. It's only the edges which are not allowed to be repeated. Okay. So once we have the definition of a path, let us now define what we call connected graphs and components. So an undirected graph is called connected if there exists a path between every pair of distinct vertices. I stress here between distinct vertices. I am not interested to I am not interested to check whether there exists a path from a node to itself, but between every pair of distinct vertices, there should exist at one path. There could be multiple paths as well, but at least one path should be there between every pair of distinct vertices. Now, what is a connected component of a graph? A connected component of a graph is the maximal connected subgraph of the graph. What does the maximal connected subgraph means? Well, it is a connected subgraph of the graph G, and it is maximal in the sense that it cannot be further extended. What does that mean? What does it mean that I can't further extend that connected subgraph? Well, that means that you can't have another subgraph of the graph G, which is also connected, such that the connected subgraph is a proper subgraph of that connected subgraph. That means it is maximal in the sense that it is not a proper subgraph of any other connected subgraph of the G. Okay. So what does this mean? Imagine I take this graph, then can I call this as the connected component, and can I call this graph as the connected component? So if I take this triangle involving D, C, and E, okay, it is not a connected component because even though it is a connected subgraph of your graph G, okay, it is a proper subgraph of this connected subgraph of the G. Okay, so that's why this is not maximal connected. So that's why the connected component of this graph is the original graph itself, because the whole graph itself is connected at the first point. So if my graph is connected at my graph G is connected at the first point, then the only connected component of the graph will be G itself. Whereas if my graph G is disconnected, then the connected component will be the collection of maximal connected subgraphs. Okay. Now let us next define cut vertex and cut edge. So cut vertex are also called as articulation point or cut critical vertices. What does it mean when I say a vertex is critical? So if I take this graph G, the node C is very critical here because if I delete this node C, then it will disconnect the entire graph. Okay, so that in that sense it is a critical vertex or an articulation point. So my definition here is the following. I will say a vertex V in a graph G is a cut vertex, and this cut vertex is defined with respect to a connected graph. So this vertex V will be called as a cut vertex if deleting the vertex V will disconnect the graph, or equivalently the number of connected components of the graph G minus V is at least one more than that of G, because if the number of connected components increases for the graph G minus V, then that is possible only if my graph G minus V becomes disconnected, because I started with a connected graph, and if even after deleting the vertex V, my new graph still has only one connected component, namely it is still connected, that means the vertex V is not a cut vertex. That means deleting the vertex V does not disconnect the graph. Similarly, I can define a critical edge, which is also called as a bridge or cut edge. So again, if I take the same graph as above and focus on this edge C and edge connecting the node C and F, then the edge connecting the node C and F is very critical, because if I delete that edge, then the whole graph gets disconnected. Okay, so that gives me the definition of a cut edge. I will say an edge is a cut edge for a connected graph if deleting that edge disconnects the graph, which is equivalent to saying that the number of connected components of the reduced graph, namely the graph obtained after removing the edge E, is at least one more than the number of connected components of G. So number of connected components of G was 1 because it was a connected graph. But now if in the new graph, namely in the graph G minus E, the number of connected components is 2 or more than 2. That means my graph got disconnected because of deleting the HE. And hence I will call the HE as a critical edge or a bridge. So that brings me to the end of this lecture. These are the references. Just to summarize, in this lecture we discussed various set theoretic operations on the graph. We discussed the various data structures which we can use to represent graphs, and we discuss about the cut vertex and the cut edge. Thank you.